All right, so we're going to talk about sequences today. Sequences and series. All right, let's go ahead and get started, guys. So today we're going to talk about a lot of kind of vocabulary and kind of all the foundations, all the tools that we'll need. And then we spend a couple of days talking about going into a little bit more detail about sequences and series. All right, so a sequence. A sequence is just basically a list of numbers. Now, usually there's a rule that goes with how we come up with the list, but essentially a sequence is just a list of numbers. We call each number in the list a term. So we talk about the terms of our sequence. If we put the terms, so we would say a sub n. The n tells us which term, a sub 1, a sub 2, first, second, third, etc. A sub n is one term. So the n tells us which term. If we put our term in braces, this tells us we're talking about the entire sequence. So when we put this in braces, we're talking about the entire list of numbers. One of these a sub n's is just one term. So an example of a sequence, and we might be familiar with this one. 1, 1, 2, 3, 5, 8, 13. What is this one? Fibonacci sequence. It's probably one of the most famous sequences in math. And they didn't talk about it directly in Donald Duck, but it is related to the golden rectangle, the golden spiral, all that kind of thing. It's actually related to quite a few things. So this would be an example, and this would be a sub 1, a sub 2, a sub 3, a sub 4, dot, dot, dot. So a sub 1 would be 1, a sub 2 would be 1, a sub 3 would be 2, etc., etc. And then if we put a sub n in braces, we'd be talking about the entire Fibonacci sequence, all the numbers. All right, we're good with what a sequence is. Okay. So let's write. We'll talk about the rules, a couple of rules for writing sequences, and do a little practice with that. So this. So we want to write the first 4 terms. And with sequences, usually, the vast majority of the time, we're going to use n is a positive integer. So for sequences, we're usually plugging positive integers into our formula for our sequence. So a sub n, for our first example, is 2n plus 5. So we want to write out the first 4 terms. So what would a sub 1 be? 2 times 1 is 2, plus 5 is 7. A sub 2, 2 times 2 is 4, plus 5 is 9. A sub 3, 11. 2 times 3 plus 5 is 11, and a sub 4, what is it? 13. 4 times 2 is 8, plus 5 is 13. So those would be our first 4 terms of that sequence. So we're plugging in a positive integer into our formula. So we usually start with 1. Let's look at another one. Let's say b sub n is 3 to the n minus 1. So b sub 1 is what? Three to the 1 minus 1, 3 to the 0, 1. B sub 2, 3 to the 2 minus 1, 3. B sub 3, 9. 3 minus 1 is 2, 3 squared is 9. And finally b sub 4, 27. 4 minus 1 is 3, 3 to the third is 27. Yes?
Wait, can you go into the recursive sequence for the, I don't get where you're getting.
For this one?
Yeah.
This is our rule. 3 to the n minus 1. Let's do one more. C sub n is minus 1 to the n power over n squared plus 1. But what's this minus 1 to the n going to make this sequence do? What's minus 1 to the 1 power? Negative 1. What's minus 1 to the second power? Positive 1. What's minus 1 to the third power? Negative 1. So it's going to make it alternate signs, positive and negative. So anytime you have negative 1 to a power to the nth power, and you're going to have an alternating sign. Yes? So let's do our first term. So c sub 1 is, I'm going to write these out, minus 1 to the 1 over 1 squared plus 1, which is going to be negative 1 half. C2 would be minus 1 squared times 2 squared plus 1, which is 1/5. C sub 3, negative 1 to the third power over 3 squared plus 1, negative 1/10. And C sub 4, minus 1 to the fourth power over 4 squared plus 1. And I get a positive 1/17. So those would be our first 4 terms. We can also have, so we call this kind of formula for our nth term an explicit formula. Yes.
If you're doing this in the public or something, you would do 4 and find out 4.
It would just it would tell you how many
Oh.
to find. So for this one, we just wanted 4. We call these explicit formulas, where we can just plug in our number and get our term. We can also have a recursive formula. So an example of a recursive formula is something like this. So for a recursive formula, we're using previous terms to find our next terms. So what this is telling us to do is take the previous term, multiply it by 3, and add 2. And we have to get somewhere to start, so we start with a sub 1. So a sub 2 would be 3 times the previous term, 5 plus 2, which is 17. A sub 3, 3, and we want to plug in the previous term, times 17, plus 2, and we get, what is that, 53? And a sub 4 will be 3 times the previous term, plus 2, and I get 161. So we call this a recursive formula. It's telling us to plug in the previous term to get the new term. Yes? We'll do, with the special kinds, we will do that. So there's a couple special kinds of sequences where we will be able to find the rule because we'll know a little more information about it. Okay? Right. All right, questions so far? All right, a lot of sequences involve factorials. Do you remember what a factorial is? Exclamation point. So n factorial is how we write it. And how do we find a factorial? What does it tell us to do? Are we adding? Multiply, right? Multiply, and what are we multiplying? All the numbers. So the way I usually write is 1 times 2 times 3 times 4, dot, 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 all the way up to n. So we're multiplying all the numbers that come before n. That's how we're going to do a factorial. This shows up a lot in a lot of sequences. And a special case, 0 factorial equals 1. Always. Otherwise, things don't work out the way they should work out. Let's write out a few factorials. 0 factorial we said was 1. What's 1 factorial? 1. 2 factorial? 2. 3 factorial? 6. Whoops. 4 factorial? 24. 5 factorial? 120. 6 factorial? 720. They get big really fast. All right, what would be the difference? Let me ask you a question. What would be the difference between this and this? What's the difference between these two? What do you think, Nikki? Yes, so the first one is saying find the factorial of n and multiply by 2. So this is 2 times n factorial. What is this telling us to do? Factorial of 2n. This equals 1 times 2 times 3 times dot 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 all the way up to 2n. So these two, make sure when you're working on the problems you notice where the parentheses are, how these two are different. All right, let's do a little practice with factorials. They'll show up quite a bit. Let's write the first 4 terms of this sequence. A sub n equals n squared over n factorial. So a sub 1 is 1 squared over 1 factorial, which equals 1. A sub 2, 2 squared over 2 factorial, which is 2 squared is 4, 2 factorial is 2, so this turns out to be 2. A sub 3 is 3 squared over 3 factorial, which is 9 over 6, which reduces to 3 halves. And a sub 4, 4 squared over 4 factorial. So we get 16 over 24, which reduces to 2/3. So that would be the first 4 terms of that sequence. All right, questions there? Okay, let's talk about how we simplify. simplify factorials. So what if we had something like, now our calculator will do these for us, but factorials are really easy to work with without our calculator. 10 factorial over 2 factorial times 8 factorial. And we want to evaluate this. We want to simplify this. So what we can always do with this is just write out what this is telling us. This is 1 times 2 times 3 all the way up to 10. And I'm going to write a few more. I'm going to write times 8 times 9 times 10. 2 factorial is 1 times 2. And 8 factorial is 1 times 2 times ... all the way up to 8. Well, what can we do with this 1 times 2 times ... up to 8 on the numerator and the denominator? Cancel them out. We're multiplying, so we can cancel those out. I can take this 2 and divide it into this 10. Turn that into a 5, and that's 9 times 5 equals 45. And the other way that we can think of this is 10 factorial is 8 factorial, 1 times 2 times 3 all the way up to 8, times 9 times 10. And that's over 2 factorial times 8 factorial. And what we're doing is canceling out that 8 factorial. And the 2 factorial is just 2. We cancel that with the 5. And we get 45. So just another way to think of that. Yes?
For the top, when you pass it to 10, how do you pass that one?
Oh, because I have this 2 in the denominator, so I just divided the 10 by 2 to get that 5. All right, let's look at one that's a little trickier. How about n factorial? I'm going to change the page here. All right, let's take a look at this. We don't have numbers this time. So let's write out what n factorial is. N factorial is 1 times 2 times 3 times ... all the way up to n. And n plus 1 factorial is telling us to multiply all the numbers that are less than n plus 1. So doesn't that tell us to multiply up to n times n plus 1? Isn't n 1 less than n plus 1? And we can do all this, the 1 times 2 all the way to n. In the numerator and denominator cancel out. And that just gives us 1 over n plus 1. Because the n plus 1 factorial is telling us to multiply all the numbers that are less than n plus 1. Well, n is 1 less. We have to go through all the numbers that are less than n plus 1. So n is less than n plus 1. So that lets us cancel that out. All right, questions on that example? Yes? Because everything in the numerator cancel. So if, for example, if it helps you can think about just plugging in numbers. So let's say n is 10. So if n is 10, if it helps you think about it. So the numerator is telling us to do 1 times 2 times 3 times ... all the way up to 10. The denominator is telling us to do 1 times 2 times 3 times ... all the way up to times 10 times 11. Well, all of these cancel out. And I'm left with just 1. When I cancel this out, I'm just left with 1 in the numerator. And just the n plus 1, whatever's left on the bottom is the n plus 1. I just did that, the same thing there, just without numbers. So if it helps you think about numbers, just plug some numbers in to see if what you're doing makes sense with the numbers. All right, let's look at one more. It's a little trickier. How about n plus 1 factorial over n minus 1 factorial? All right, so in the numerator is telling us to multiply 2 times 3, dot, 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 dot. And all the numbers less than n plus 1, well, that's telling us n minus 1 is less than n plus 1. N is less than n plus 1, and then we go to n plus 1. And then this is the denominator telling me 1 times 2 times 3, dot, 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 all the way to n minus 1. So I'm in the numerator, I want all the numbers that are less than n plus 1. Well, n is 1 less, n minus 1 is 2 less. So I have to go through, I have to multiply all of those numbers to get to n plus 1. I can cancel those out. And I get n times n plus 1. And all I'm left with in the denominator is a 1. Yes? Well, n minus, so we could write those out. N minus 2 would be not to the right, but to the left. This would be n minus 3, n minus 2, n minus 1. And I could put those over here, n minus 3, n minus 2. Those would be to the left of n minus 1 because they're smaller than n minus 1. So they're n minus 2, n minus 3 is smaller than n minus 1, so they're down here in the numbers that are less than n minus 1. All right, questions there? All right, yes. On the top, so what the n plus 1 factorial is telling us to do is multiply all the numbers that are less than n plus 1. So if it helps, do like we did here. So if n, let's say n is 10. Guys, let's stop talking, please. Let's say n is 10. So n plus 1 is 11. So n plus 1 factorial is 1 times 2 times 3 times dot 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 times 10 times 11. So it's all the numbers that are less than n plus 1. So that's where the n and the n minus 1 came. So here is the n, is 10. There'd also be a 9 here, which is n minus 1. So that's where that, I just did that without putting numbers in there. Does that make sense? Just getting all the numbers that are less than n plus 1. Okay? All right. Let's go the other direction now. Let's say we have a sequence and we want to find a rule for it. We want a rule for the nth term. And we're given some terms of our sequence. So when we're doing this, what we want is some kind of rule that relates the term number, 1, 2, 3, 4, to the number that we have there, the 0, the 3, the 8, the 15. So, anybody see a relationship there? So what term is 0? It's the first term. So I'm just going to write 1. How is 0 related to 1? Isn't it 1 less? 0 is 1 minus 1. How about 3? Isn't that 4 minus 1? 8 is 9 minus 1. 15 is 16 minus 1? So how are these numbers, how are the 1, the 4, the 9, the 16 related to 1, 2, 3, 4? They're squared, right? They're the square roots of that. So this is 1 squared minus 1, 2 squared minus 1, 3 squared minus 1, 4 squared minus 1. So our rule could be a sub n equals n squared minus 1. So we're trying to look for a connection between the number and the term number. And when I look at this, the first thing that I see is each of these is 1 less than a perfect square. 3 is 1 less than 4, 8 is 1 less than 9, 15 is 1 less than 16. So we're kind of recognizing those, trying to recognize those patterns. All right, how about 1/2, 1/6, 1/24, 1/120th? Do we recognize those denominators? Yes? Okay, so what is that thing? 2 times 3 is, and we're multiplying by one higher number each time? What is that? Factorial, right? So this is 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial. So my rule would be a sub n equals 1 over, this is the first term, so how do we write our rule? N plus 1 factorial. All right, a little trickier on this one. All right, so what is that, the alternating signs? What are we going to have in our term? We have a positive, negative, positive, negative. So we're going to have a minus 1. Does the n power work? Minus 1 to the first power is negative, right? Negative 1. So how do we get it to be positive? What can we do to this n to turn minus 1 to the something with a 1 in it to a positive? What was it? Someone said add 1, right? So now my first term, I'd have negative 1 squared, which would be positive. For my second term, I would have negative 1 to the third power, which is negative. Third term is positive because I have negative 1 to the fourth. Okay? And how about these numbers in the numerator? 2, 3, 4, 5, 6. How are those related to the n to the term? N plus 1. Looks good to me. And in the bottom, 3, 4, 5, 6, 7. N plus 2. So that would be my rule for that sequence. And I had to do the n plus 1 because the first term was positive rather than negative. So I wanted to get to alternate, but I wanted to start with a positive. Questions there? Okay. One last idea. Summation notation. So one thing that we want to do with sequences is we end up wanting to add the terms together. And summation notation is what tells us to do that. So the way this looks is going to be the sum, I equals 1 to n, a sub I. This tells us to add. So this is telling us to add our terms. And this thing is a capital sigma, Greek letter sigma. So what this is telling us to do, sum I equals 1 to n, a sub I, is saying to add a1 plus a2 plus a3 plus dot 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 up to whatever n is. I is called the index. One is, in this case, is the lower limit. And n is the upper limit. So if n were 4, it's telling us to add 4 terms of that sequence together. A sub 1 plus a sub 2 plus a sub 3 plus a sub 4. If n were 10, it would be telling us to add 10 terms of that sequence together. So let's look at an example. The sum of I equals 1 to 4 of 3i. So this is just telling us to add together 4 terms of this sequence. So that's going to be 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4. So I starts at 1 and goes all the way up to 4. And if I calculate this out, this equals 34. 3 plus 6 plus 9 plus 12. So it's just telling us to add those terms together. We know how to find the terms. We just plug in our number there. And the sum, the sigma, is telling us to add them together. Okay, we good there? We're going to do, after today, we'll do some work with some special kinds of series. We're adding together certain kinds of terms of sequences. And they do some, they have some nice things that happen. All right, a couple of properties, easy properties of summation notation. If I have a constant times some term, I can factor that constant out. So I could have factored this 3 out of here and just done 3 times and added together the 1, the 2, the 3, and the 4, and I would have gotten the same answer. So we can see the 3 shows up in all of these. We could factor that out. And we can add or subtract terms inside the summation, or we can do them separately. So we can keep them together inside there, or we can pull them apart and do them separately. So just a couple of ways, a couple of nice things that simplifies working with series. And then the last thing that we're going to do is talk about an infinite series. So there's one kind of series that we'll talk about where we add together an infinite number of terms. And depending on how it's set up, we can actually get an answer for that. Okay, we good here? So we said that the sum I equals 1 to n, a sub I, is a series. If I let my upper limit equal infinity, that's an infinite series. And depending on how we set the infinite series up, we can actually add up an infinite number of terms and we actually get an answer. We'll talk about those kinds of series on block day. And we call this the sum I equals 1 to n of a sub I is the nth partial sum of the infinite series. So we're just adding a certain number of terms of the infinite series. So if we have an infinite series and we only add a certain number of terms, we call that the partial sum. So the fourth partial sum would tell us to add up 4 terms. The fifth partial sum would tell us to add up 5 terms. The 10th partial sum would tell us to add up 10 terms. And sometimes when we have an infinite series, we can actually come up with an answer. We'll talk about this more a little later, but let's look at this example. So for this infinite series, we want to add powers of 1 over 10. We want to add an infinite number of those together. So let's write out a few terms. 1/10 to the first power is 1/10, plus 1/10 to the second power is 100, plus 1/1000, plus 1 10,000th, plus, and we keep going. What's 1/10 as a decimal? 0.1. 1/100th as a decimal? 0.01. 0.001. If I add up 0.1 plus 0.01 plus 0.001 plus 0.0001, what do I get? 0.1, 1, 1, 1, 1. 0.1 repeating. So if we add up an infinite number of powers of 1/10, we get the repeating decimal 0.11111. Kind of an interesting idea. You can add up an infinite number of numbers and get a number that's actually kind of small. 0.111 is not really big. All right, questions there? Okay. So our homework, calculating the terms of sequences, finding rules for sequences, using those factorials a little bit. EOE every other even. All right, there you go.